All right, so here we're looking at what we call transformations of graphs, which means when we have a function and looking at how multiplying or adding some parameter to it at some point, how it changes the shape of the graph. And let's just get straight into here. I have a very simple function, a quadratic function, x squared. All right, and that's what's shown right here in blue. All right, this is f of x. That's the equation in function notation. There's the actual equation, x squared. All right, I translate it. Now, the word translate, if we translate a function in terms of graphs, that means we slide it around, we move the function up, down, left, or right, but we're not stretching it, we're not rotating it, we're not reflecting it. About as simple as a transformation as it gets. And one way of showing a translation is with a vector. Now, later on this course, we'll work with vectors a lot more. But in general, a translation vector has two numbers, and the number at the top, that tells us the horizontal change, and the number at the bottom tells us the vertical change. So that 3 there, that positive 3, means I want to imagine this quadratic function moving 3 to the right, and that negative 2 means I also want to imagine it moving down 2. And it's a pretty quick way of showing these basic transformations, or translations, I should say here. And so I just want to imagine this quadratic function move 3 to the right and down 2. Which means this vertex, instead of being at the origin, is going to be 3 to the right and 2 down. It's now right here at 3, 2. And I can just do the same thing to any point. For example, this point here, instead of being at 1, 1, move it 3 to the right and 2 down. It's right here. And do that a few more times, and I quickly get a carbon copy of my original shape. It's congruent to my original shape, but it's been translated. All right, and so now this equation here, what do I call it? Well, that's the second part. I want to write the equation of this both in function notation as well as an explicit equation. So in function notation, let me go back to what I had in blue. I gave you f of x. Well, when we translate something to the right or the left, we add or subtract just to the x, just to the input. And when we translate a function to the right, we actually need to subtract just the x. So if I write this part, y equals f of x minus 3, just that represents the translation 3 to the right. Also want to move it down 2, and to do that we subtract 2 from the entire function. And so here's my answer in function notation, which I'll write right here, f of x minus 3 minus 2. However, what's the actual equation? Because if I look back up here, I have f of x, that's the equation in function notation, but the explicit equation is x squared. And so in this case, f of x, again, is still x squared. So everywhere there was an x, all I do was square it. Here, instead of an x, I have x minus 3. And so this equation is going to be x minus 3 all squared. However, I also have this minus 2 here. That's separate from the function, so I should have a minus 2 here separate from the part that's being squared. And so I have my equation in function notation. I have the actual explicit equation. It's only this equation you can actually graph in your GDC. All right. Before I go on, keep in mind, ideally you've been introduced to quadratic functions already, so these ideas of translating it around are nothing new, really, just that showing it with a vector. This translation vector up here is new. All right, here I have a different function. It's g of x. What's the equation? Doesn't really matter, because I'm not asking for the equation. I just want to understand these transformations. But what I see here in blue is g of x. All right. And I can see it goes through these points quite nicely. So in green, I want to show negative 2g of x. So what does that represent? Y equals, make that a little bit thinner, negative 2 times g of x. Well, when we take a function like g of x and we multiply by the whole function by a value, that is a vertical stretch. And it's actually doing two things. This is both, the negative will reflect in the x-axis. I also call that a vertical reflection. And the 2 part means it's also a vertical stretch, or a vertical expansion, we can call it. by a scale factor of 2, which means every y coordinate of this graph is being doubled, is being multiplied by 2. And again, ideally, we've seen these things with quadratics from other courses. And so let's see what that looks like here. I have my graph of g of x. If I reflect it in the x-axis, that's pretty easy to do. Instead of this point being 2 up, it's 2 down. And so I have this. Then I have the stretch, which means all those points are now, all the y coordinates are being doubled. Every y coordinate is being multiplied by 2. That's what a vertical stretch by a scale factor of 2 means, which means this point here, instead of being 2 down, I double it, so it's now 4 down. These points here will not change. They'll be invariant because their y coordinates are 0, and 0 times anything is still 0. And so I have those 2 points, the end points stay where they are. Everything else, the y coordinates double. And so I have a shape that looks like this. And there's my graph in green of negative 2 g of x. And then also in red, I have g of negative 2x. So I'm still multiplying by negative 2, but instead of the entire function being multiplied by negative 2, just the input, just the x's. And so what is happening here? Well, these are horizontal stretches. So y equals g of negative 2x. In this case, I have a reflection in the y-axis. Also, I call that a horizontal reflection. As well, there's a horizontal stretch. It's actually a compression. It's being squished, not the best word, but horizontal compression by a scale factor of not 2, but 1 over 2. All my x coordinates are being divided by 2. And so let me show you what it looks like here. Again, the order I look at these doesn't matter. So first I'm going to reflect it in the x-axis. We're going back to function g of x. Everything I'm writing about here is with relation to g of x, which I have here in blue. So going back here, the horizontal reflection means I imagine a mirror right on the y-axis. And so this point here, instead of being 4 to the right, is 4 to the left. Instead of being 2 to the right, this is 2 to the left. And I have a copy, a reflection, just like this. Actually, I'm going to make this a dashed line. I'll clean this up a bit, because I'm not done yet, so I'll just do this. This is my horizontal reflection, or my reflection in the x-axis. It's also, I need to think about my horizontal compression by a scale factor of a half. It's horizontal, so it's just the x coordinates that are being stretched, but the scale factor is the reciprocal of 2. There was a 2 here, but it's the reciprocal, that's the scale factor. So all my x coordinates are being multiplied by a half, which means all my x coordinates are being divided by 2, which means, for example, this point right here, instead of being at negative 4, it's now going to be at negative 2. And this point here, this vertex I had right above it, instead of being 2 to the left, divide that by 2 is 1 to the left. But it's still going to start at that 0, 0, because the x coordinate is 0, 0 multiplied or divided by anything is still 0. And so in the end, I have a shape that looks like this. It's been reflected horizontally, or in the y-axis, and a horizontal compression. And that is my graph of g of negative 2x. And before I move on, let me just switch here into Desmos, a little dynamic illustration here. So here's that same graph. You can actually see the equation, but that doesn't matter. What you see here in red is the exact same thing, but the whole function g is being multiplied by a, and just x is being multiplied by b, but right now you can see a and b are both 1. If I make a larger, we can see that vertical stretch, and perhaps you can see why we call it a vertical stretch. And if I go all the way to here, call this a vertical stretch by a scale factor of 4. Every y value has been multiplied by 4. If I bring it closer to 0, in fact, when I get less than 1, like right here, this is a vertical stretch by a scale factor of 1/2. All my y values are being multiplied by 0.5 or divided by 2. And as soon as I bring a into the negatives, I can see that I have a reflection in the x-axis, and now a stretch. If I go all the way to negative 4, I can see my original function has been reflected and stretched, all vertically. Whereas if I put this up to 1, which means the a is not doing anything. If I do the same thing with b, if I make b larger, it gets compressed. And again, the larger b is, the more my x coordinates are being divided. For example, at this point, every x coordinate of that semicircle is being divided by 4. And if I make it closer to 0, it gets expanded horizontally. When I get, for example, right here, where my b value is a half, that means my horizontal stretch is actually by a scale factor of 2. Everything's been doubled. And when I bring it into the negatives, it gets reflected as well. And so these are horizontal stretches and reflections. These are vertical stretches and reflections. All right, with that said, one more question about this. The point 2, 2 is on the graph of g of x. Yep, it's right there. Where will it be on negative 2g of negative 2x? And so there's a few ways I can do it. I'm going to do this a little less visually, just, I don't know, because. And so I know that 2, 2 is on g of x. Well, if I look right here, I got a number of transformations. I'm going to do them one at a time. I'm first going to focus on just the negative in the front. So if I look at negative g of x, that is a vertical reflection or a reflection in the x-axis. So my x-coordinate will not change. My y-coordinate will become negative 2. And then I want to take into account the 2 here. So I'm also doubling that. In fact, I don't have a lot of space here. I'm going to give myself, I'm going to do the 2 steps in one. I'm going to look at negative 2g of x. Just that part, because we've already talked about this actually. And so that is identical to what I have up here. So it's a reflection and it's stretched. And so instead of being 2 above, it's 4 below. And then if I take that and look at the whole thing, negative 2g of negative 2x, just this part here is what we did here. It's a reflection in the y-axis and compressed horizontally by a scale factor of a half. And so now I'm looking back at this point right here, or this point right here, I really should say. And so from that 2, negative 4, I want to reflect it horizontally. So instead of being at 2, it's now at negative 2. But then I also want to compress it by a scale factor of a half, which means instead of being at negative 2, it's at negative 1. But the y-coordinate will not change because those are both vertical transformations, I should say. And there's my answer. Now that's it. That was a very numeric approach. You may not like that. You may prefer to just take that point, and you could easily just take this point that I highlighted in orange and perform on those transformations into it, and you should end at negative 1, negative 4. In fact, why don't I do it right here? If I make A negative 2 and B negative 2, we have the equation asked us to figure out, and there is that point, negative 1, negative 4. All right. Lastly, I have a quadratic function with these transformations applied to it. I want to find the equation of the image function. I want to find the equation of the function after it's been transformed. And so let's think of what these mean. I have a reflection in the x-axis, a reflection in the y-axis, and a vertical stretch by a scale factor of a half. So let me, for a moment, let me just take this original function, this y equals negative 4x squared minus 2x plus 1, and let's call it f of x, just to make my life, sorry, a little easier for a moment. So I'll say let f of x equals negative 4x squared minus 2x plus 1. Let's just call that f of x for a moment, which means that reflection in the y-axis I can show as just negative f of x. Make the whole thing negative, the reflection in the x-axis. Sorry, that's what I did first. The reflection in the y-axis, that horizontal reflection, that's when I make just the x negative, so I have a negative here. That's just the reflection in the y-axis. And then finally, my vertical stretch by a scale factor of a half. All I got to do is take this and multiply the whole thing by a half. So let me give myself a bit more space and put a little 1/2 here. And so now all those transformations I wrote, I've described in function notation. And so what's now the actual equation? Well, let's think about how this here relates to this up here. If I look at my original equation, negative 4x squared minus 2x plus 1, I call that f of x. Everywhere there was an x, I now want to change that to negative x. And so I'm going to write this as negative 4. Instead of x squared, it's negative x squared. Minus 2 times, instead of x, it's negative x plus 1. That orange highlighter is kind of ugly, but oh well. So what I have there, that covers just this part. This is all of this. But it's also being multiplied by -1/2. This whole thing here is being multiplied by -1/2. And so I need to put some brackets around this and multiply by -1/2. Now, this is okay. It's just needlessly messy, but I want to clean this up. But this is the equation of -4x² minus 2x plus 1 after the reflection in the x-axis, the y-axis, and that vertical stretch by a scale factor of 1/2. But let's clean this up. So now at this point, let me just work from the inside of the brackets out. So I'll leave the -1/2 for a moment. Right here, -x² is x². Negative times a negative is a positive, so I can write this as -4x². I don't need that -x in brackets. Over here, -2 times -x is +2x plus 1. Okay, that's already a bit nicer. Now let me distribute this -1/2. And so -1/2 times -4 is +2, so +2x². -1/2 times 2 is -1, so -x. And -1/2 times 1 is -1/2. And there's the equation in sort of a standard form for a quadratic equation. Which, if I just switch to Desmos here, let me turn this off. So here's the function that we started with, now graphed. This is the -4x² minus 2x plus 1. And if I step by step show these transformations, first the vertical reflection looks like that. And so that's just the vertical reflection or the reflection in the x-axis. So I'm going to turn off now from my original function now, because from that I want to reflect it horizontally, which is what you see right here. Notice instead of everything to the left and the right swapped around to get that. So now what you see there is both those reflections done, and then finally the compression, vertical compression, all my y coordinates are being multiplied by 1/2. And that's the equation we ended up with. We didn't have to sketch it, but the important part is understanding those transformations. So yeah, I'm done.